Friends, let me introduce myself. I am Professor C.S.P. Rao, working as Professor in the Department of Mechanical Engineering of National Institute of Technology. I have around 20 years of experience, and I've been working in the area of manufacturing and computer integrated manufacturing for the last more than 15 years. Let us discuss the importance of manufacturing. Our nation GDP depends on two important areas. One is manufacturing, agriculture, services. In the manufacturing, how we produce goods, it is all about that only. And the word manufacturing, India is now gradually picking up well-to-do business in manufacturing. Let us discuss a brief history of manufacturing and how the manufacturing from the hardcore hand-based manufacturing to computer integrated manufacturing, how it was developed. Let us all discuss that in this introductory class. Before we discuss the computer integrated manufacturing, a systematic approach I would like to adopt in all of my lectures. The first series of that is only the introduction to manufacturing, how the manufacturing era was started and how developments took place in this area, and how automation was helped in manufacturing, how computers helped in manufacturing, how computer integrated manufacturing is achieved today. And the components of computer integrated manufacturing are the sub areas that are related to computer integrated manufacturing we discuss in the further classes to come. And the entire course is encapsulated as computer integrated manufacturing, which is comprising of around 10 lectures with all interactive programs and other things. And first of it is Introduction to Manufacturing. So let me discuss the history of manufacturing and other developments in manufacturing. In detail, this topic as followed in these sections: manufacturing history, production systems, automation in production systems, labor in production systems, automation principles and strategies, manufacturing industries, products, manufacturing operations, production facilities, product and production relationships, lean manufacturing, lean production systems, and manufacturing matrices or mathematical modeling of manufacturing systems. Manufacturing has been a human activity for a very long time. Ancient man produced stone articles by using his muscular power. Earlier manufacturing remained in the hands of artisans and their apprentices, and their earlier developments in manufacturing took place in their supervision. Probably the copper is the first metal melted by man. Excavations of Mohenjo-daro and Harappa shows the metal and jewelry work. There are examples in Greek and Roman civilizations that their craftsmen used casting processes as well. Inventions of copper, bronze, and then Iron Age converted ancient civilization into Indus Valley, China, Egypt, Mesopotamia, and Babylon civilizations. Concept of machining is also very old. It is believed that the idea of lathe, the so-called turning machine, has been derived from the potter's wheel that existed before 2500 BC. The round groove marks on wooden bowls shows that turning was practiced as early as 1700 BC and was perfected before 6th century. The concept of tool angles is also not new. The primitive man started thinking of tools in which a proper shaped tool used to be tied with a wooden branch. Later, the stone pieces was replaced by metallic pieces. The idea of rotating stone wheel for production sharp edges brought the concept of grinding. Wheels mounted on a spindle with crank were started appearing around 850 AD. The earliest known machine tool, that is lathe, 1400 AD. Earlier, alternating motion was given to wooden workpiece and tool was kept stationary on hands. Later, a continuous unidirectional motion was attempted by winding an endless rope around a spindle and passing it over a flywheel which was rotating by hand. Wooden plank lathe, so named lathe, was derived. Drilling was carried by winding a cord on the sharp metallic linear piece and attaching its end to the rod. The art of forge welding was attempted during 2500 BC, but it took a reasonably better shape around 1000 BC. Use of filler material started around 2500 BC. A wire drawing setup in use around 1000 BC is shown in this figure. After the discovery of iron, the development of hot forging, forge welding and grinding became imperative. The concept of grinding was, although old, but giving it unidirectional motion took many years. Many distinguishing features of modern machine tools were anticipated in design by small-scale clock makers. During 1480 AD, a German clock maker introduced the concept of screw cutting on lathe machine. After a long, around 1780 AD, Ramsden produced an accurate screw thread cutting lathe by producing a series of screw threads. During the latter half of 17th century, use of timber was replaced by coal for iron smelting, but it could not lead to good results because of use of coal was surface coal. Thus, deeper mining became a necessity, but was a problem as no higher capacity pumps were not available. Newcomen's engine was installed in coal mines, but could not solve the purpose because of their huge size and inefficiency. James Watt, 1762 AD, tried to solve the problem by using his steam engine up to a maximum. Watt patented 1769 AD his engine. However, he failed to develop full-size engine. His problem was to get accurate piston cylinder assembly. John Wilkinson, 1728 to 1808 AD, the great iron maker, developed various kinds of water-powered boring machines for producing iron cannons. He was the only cylinder maker who could face the challenges made by Watt. In 1775 AD, Watt's attempt was successful. Later, Wilkinson used Watt's engine to drive his boring machines. By the end of 18th century, the steam engine power was available in large quantities at many locations, which caused first industrial revolution. This led to the growth of production and mechanization. The Soho foundry in London was established in 1796 AD with steam engines was considered as engineering workshop of that time. By 1820 AD, power driven by steam and such steam power driven machine tools were ready for the sale. Now the need of high strength materials was felt, which was met by carbon steels. Liebig, 1831 AD, could perfectly analyze and determine the effect of carbon on the strength of the steel. This started the age of steels, and it became possible to produce rigid and precision machines. Henry Maudslay, 1771 to 1831 AD, brought several new concepts in machine tool. He introduced the tool, slide, and rest was Henry Maudslay, 1771 to 1831 AD, brought several new concepts in machine tool design. He introduced the tool slide and rest with tool head in 1794 AD. It was equipped with lead screw and had provision for tap turning. He also produced a number of screw cutting machines. In 1805 AD, first micrometer was designed by him. During 1825 to 1865 AD, machine tools like planing, shaping, drilling, punching, slotting, milling, etc. were developed. The need for strong marine vessel led to introduction of rolling mills that produced iron flats for ships, which crossed the Atlantic in 1883 AD. These rolled material also met the requirement for multi-storied buildings, etc. By the mid of 19th century, Britain became the leading country in science and technology. True industrial revolution started when the concept of mass production was introduced in 1748 AD to lower the production costs so that the benefits of engineering could reach to the common man. Proliferation of machines started and a large number of special purpose machines, automatic and semi-automatic machines were designed and developed. The trend was to move towards mechanization and hard automation. Whitney introduced the concept of interchangeability in the end of 18th century. This needed more close tolerances, therefore need for high-speed stone tools. Felt and development in precision grinding took place around 1980. Significant improvement in welding processes also took place during this time, and use of metallic molds and patterns came into scene so that precise casting would be achieved. Polymer products were developed during 1925 to 1950 AD due to requirement of high strength to weight ratios. Introduction of hard temperature resistant material led to the development of various unconventional machining processes during 60s. Second industrial revolution started during mid of 20th century with the enormous growth in solid state electronics and computers that can perform tasks very rapidly, efficiently with lower costs. In this age, attempt was to enhance and sometimes even replace the mental efforts. The trend was now to move towards flexible automation. Today, the era of mass production and hard automation is going away and is being replaced by batch production and flexible automation concepts. The first step in this direction is the development of numerical control machine tool, in which the motion of the slides is controlled by numericals and letters. The microprocessor-based system and feedback devices provide better accuracy and precision in numerical control systems. In this slide, you can see the historical developments of manufacturing processes, which was summarized as below. 1400 BC, the material was found as gold, silver, copper, and the casting method or the metal manufacturing method was used as clay mold casting, and cold forging is also being adopted for manufacturing of jewelry with these materials, and machining was done by stone tools. 2500 BC, only brazing and welding was done, and you can read the other developmental processes as follows listed in this table. Now let us now discuss the modern manufacturing approaches and technologies. In this, we use a word called as automation. What is this automation? We do the process automation, automated equipment instead of labor, using labor. Material handling technologies, because of manufacturing usually involves a sequence of activities, and manufacturing system integration and coordination of multiple automated and manual workstations. Flexible automation to compete in low volume, high product mix categories, quality programs to achieve the high quality expected by today's customers. SIM, computer integrated manufacturing to integrate design, production and logistics. Lean production, more work with fewer resources. So now let us define what is called as production system. A collection of people, equipment and procedures organized to accomplish the manufacturing operation of a company is called the production system. Two categories of the production systems in which facilities are part of it and manufacturing support systems are part of it. The factory and the equipment in the facility and the way the facility is organized. The facility organized, we call that as plant layout. All of these are called as facilities. Manufacturing support systems, the set of procedures used by the company to manage production and to solve technical and logistic problems in ordering materials, moving work through the factory and ensuring that products meet quality standards with the required schedules. Manufacturing support systems in collaboration with facilities, factory equipment, we call this as a production system. The facilities include the factory, production machines and tooling, material handling equipment, inspection equipment and computer system that control the manufacturing operations, all these called as facilities. Plant layout, the way the equipment is physically arranged on the shop floor or in the factory is called as plant layout or facility location. Manufacturing systems, logical grouping of equipment and workers in the factory. It can be in production line or standalone workstations or workstations alone. Manufacturing systems, you can classify them as three categories in terms of human participation in the processes performed in the manufacturing system. One is manual work systems. A worker performing one or more tasks without the aid of power tools, but sometimes using hand tools. Worker machine system. A worker operating the powered equipment is called as worker machine system. Automated system. A processes performed by a machine without direct participation of a human being. The schematic of manual work system is look like this. We have the process and the process is being done by the worker with the help of hand tools and etc. Worker machine system, you can see that the process is being done by the worker with the help of a machine. Automated system, still the process being controlled by automated machine and periodic worker attention is only required for machine and for maintenance and etc. Now let us discuss the word manufacturing and further on manufacturing. The word manufacturing is derived from two Latin words. Manus means hand, factious means make. The combination of making or made by hand, anything made by hand is called as manufacturing. Made by hand accurately described as the fabrication method. The fabrication methods that are used were the English word manufacture was first coined in 1567 AD to replace fabrication or made by hand. That's how the manufacture or manufacturing comes into existence. Most manufacturing operations are accomplished by mechanized and automated equipment that is supervised by human workers. Applications of physical and chemical processes to alter the geometry properties and the appearances of a starting materials to make parts or products, and manufacturing also includes assembly, almost always carried out as a sequence of operations. Transformation of materials into items of great value by means of one or more processing and or assembly operations. Manufacturing adds value to the material by changing its shape or properties or by combining it with other materials. The quantity of products, let us say Q, made by a factory has an important influence on the way its people, facilities and procedures are organized. Annual production quantities can be classified into three categories. If the annual production quantity is less than 100 units per annum, we call them as low production systems. When the annual production quantity is from 100 to 10,000 units per annum, we call that as medium production industry. And if the annual production of units are more than 10,000 per annum, we call that as high production industry or high production system. The product variety P refer to different product types or models produced given plant. Different products have different features. They are intended for different markets. Some have more parts than others. The number of different product types made each year in a factory can be counted. When the number of product types made in a factory is very high, this indicates high product variety. Although P is a quantitative parameter, it is much less than Q because details on how much the designs differ is not captured simply by the number of different designs. Soft product variety, a small difference between products, example between car models made on same production line with many common parts among models. If you take a car manufacturing unit, let us say the Maruti 800, Zen Alto or Estilo, something like that. All of them are more or less made on the same production line, in which there are several components are common. Very few components like body shape and other things may differ. So this variety is soft product variety. This variety is called as soft product variety. Hard product variety. Products differ completely, substantially. Example, a small car and a large truck with fewer common parts. The common parts are very, very few in that. Whereas in the soft product variety, the common parts are large in number and different parts are small in number. Manufacturing processor, we can divide them as processing operations and assembly operations. Processing operations transform the work material from one state of completion to a most advanced state, which we call as value addition. Operations that change the geometry, property or appearance of the starting material. Second one is assembly operation. Two or more components joined together permanently, temporarily to create a new entity which is called as assembly. Complete classification of manufacturing processes, both processing operations and assembly operations, and in which processing operations, shaping operations, property enhancing processes, surface processing operations, etc., etc. Processing operations alter a material shape, physical properties or appearance in order to add value. Three categories of processing operations are shaping operations, alter the geometry of the starting work material. You take lathe operations, the operations performed on a lathe, they are all shaping operations. Property enhanced operations, improve physical properties without changing the shape. Physical properties like surface hardness, strength, surface roughness, surface finish, all of them comes under this thing. Properties that enhancing operations, improve physical properties without changing the shape. Surface processing operations to clean, treat, coat or deposit material on exterior surface of the work. Two or more separate parts are joined to form a new entity is assembly operation. Types of assembly operations can be joining processes, create a permanent joint, welding, brazing, soldering, adhesive bonding, mechanical assembly by means of application of fastenings or fasteners, rivets, etc., threaded fasteners, press fittings, expansion fits, etc. People, equipment and processes and procedures are used for the combination of materials and processes that constitute a firm's manufacturing operations. A manufacturing firm must have systems and procedures to efficiently accomplish its type of production. Two categories of production systems. One is production facilities, manufacturing support systems. Both categories include people, the factory, production equipment and material handling systems. And production facilities like touch the product include the way the equipment is arranged in the factory or the plant layout. Equipment usually organized into logical groupings called manufacturing systems. Examples: automated production line or manufacturing cell consisting of industrial robot or two machine tools like that. Product variety, a number of different product or product designs or types is called as product variety. Hard product variety, the product differ differently or differ greatly. Few common components are so common in an assembly. Soft product variety, small difference between products and many common components are there and less different parts are there. Low production quantity, we call them Q low, is job shop industry. A job shop makes low quantity of specialized and customized products. In a job shop industry, the kind of components the kind of products we get are low in number and the product variety is very high. Products are typically very complex like machine tools, gas turbines, compressors, manufacturing many big industries like BHEL Hyderabad or BHEL Haridwar, where they manufacture these units. Okay, such kind of industries comes under the category of job shop industries. The equipment used in job shop is very general purpose machine tools are used. Plant layouts are fixed position layout and process layout. Two different types of facility depending on product varieties. Batch production suited to hard product variety. Setups required between batches. Cellular manufacturing suited to soft product variety. Worker cells organized to process parts without setups between different part sizes. Medium production quantities. One is batch production. A batch of a given product is produced and then the facility is changed over to produce another part. Changeover times, setup times are required. Typical layout is process layout and hard product variety. Cellular manufacturing, a mixture of products is made with significant changeover times between products. Typical layout is cellular layout, soft product variety. Quantity production, the equipment is dedicated to the manufacturing of one product only or mass production. Standard machines tooled for high production like stamping presses, molding machines, etc. Typical layout is a process layout or a continuous process layout. Flow line production or multiple workstations are arranged in sequence. Product requires multiple processing or assembly steps. Product layout is most common. Facility is organized in the most efficient way to serve the particular mission of a plant and depends on type of product manufactured, production quantity, product variety. The layouts are classified as fixed position layout, process layout, cellular layout, product layout. You see here manufacturing of an aircraft or air engine comes under fixed position layout. Manufacturing of satellite, assembling of big missiles, all of them are fixed position layouts. Ship manufacturing is a fixed position layout. Next is process layout. You can see here the same kind of workstations or machines kept in one section. Let us say all the lathe machines put together is called as turning section, and all drilling of machines put together a drilling section and grinding section, like that. So this kind of all the machines kept in these sections, and the sections are well connected by material handling techniques or methods, and such a layout is called as process layout. You can see that in this figure. Cellular layout. Cellular layout is one in which the combination of machine tools that are required to produce a variety of parts are kept in a particular sequence of order, and the arrangement of that is called as cellular layout, and the manufacturing is called as cellular manufacturing, and the facility is called as cell. Product layout. The product layout is all the workers all the machines are kept in sequence of the processes that the part should undergo, and same part variety is used, only part variety is only one, and the production volume is very, very high in this kind of layouts of systems. And we can now have a very good relation, make out a very, very good relation between the P and Q. That means product variety and quantity, the volume of the production. On x-axis we can lay out Q or P, both. In some of the textbooks we can observe the other way also. On x-axis P and y-axis Q, and mostly on x-axis Q is used and y-axis P is used. Product variety is on y-axis. If you see that mass production systems where the product variety is very, very low and the production volume is more than 10,000, so on this extreme corner you can see that modern mass production system occupies. Here in this, the job shop occupies the foremost this corner opposite to that, and towards more P, because product variety is more in job shops, whereas product volume is very less in job shop. Mass production systems of single parts on a single machine or small number of machines we can have, and typically involves standard machines equipped with special toolings. Equipment is dedicated full time to the production of one part or production type. Typical layouts used in quantity production are process layout and cellular layouts. Flow line production, multiple machines or workstations are arranged in sequence like production lines. Product is complex, requires multiple processing or assembly operations. Work units are physically moved through the sequence to complete the product. Workstations and equipment are designed specifically for the product to maximize efficiency. Now let us move to the second part, that is manufacturing support systems. A company must organize itself to design the processes and equipment, plan and control production, and satisfy the product quality requirements. Accomplished by manufacturing support systems, people and procedures by which a company manages its production operations. Typical departments of support systems are manufacturing engineering, production planning and control, PPC, quality control. Manufacturing support systems involve a cycle of information processing activities that consist of four functions. 1. Business functions: sales, marketing, order entity, cost accounting, customer billing. Product design, research and development, design engineering, prototype shop. Manufacturing planning indicates process planning, production planning, MRP, capacity planning. Manufacturing control includes shop floor control, inventory control, quality control. Information processing cycle in a manufacturing support system, you can see it here. The product design, this wheel contains four important areas: manufacturing planning, control, business functions, and product design. They in turn interact with the production system facilities, and the whole thing is activated, started moving at the customer order. Automation in production systems. Automation has been adopted in production systems to make it easy, and management is without intervention of human beings. Two categories of automation in the production systems are popular. One is automation of manufacturing systems in the factory. The second one is computerization of manufacturing support systems. The two categories overlap because of manufacturing support systems are well connected to the factory management systems or computer integrated manufacturing, which encompasses the areas of manufacturing support systems and potential computerization of applications, factory facilities or potential automation applications. This is the overall concept of computer integrated manufacturing, and the discussion on automated manufacturing systems continues. You can say there are several examples of this are automated machine tools, transfer lines, automated assembly machines, industrial robots that perform processing and assembly operations, automated material handling and storage devices or systems, automated inspection systems, automated material handling systems, etc. There are all various automated systems available in the automated manufacturing systems. The PQ diagram still continues of discussion, where for mass production systems where the manufacturing units or the production volume is more than 10,000 components with product variety is equal to 1, we can go for fixed automation. The completely mass production systems can be done by fixed automation manufacturing systems. Coming to the other end, where you have job shop systems, we can implement a job shop as a programmable automation system. Programmable automation units or equipment can be implemented or incorporated in a job shop environment, where a job shop is altered to a programmable automation unit to enhance the overall production capability, including the variety. Automated manufacturing systems, we can probably have three different varieties. One is fixed automation, programmable automation, flexible automation. The fixed automation includes a manufacturing system in which the sequence of processing operations is fixed by equipment configuration. Typical features are suited to high production quantities, high initial investment for customer engineered equipment, high production rates, relatively inflexible in accommodating product variety. Programmable automation, a manufacturing system designed with the capability to change the sequence of operations to accommodate different product configurations. Typical features are high investment in general purpose equipment, lower production rates than fixed automation, flexibility to deal with variety and changes in product configurations, most suitable for batch production. Physical setup and part program must be changed between jobs. Flexible automation, an extension of programmable automation in which the system is capable of changing power from one job to the next with no loss of time between jobs. Typical features of this flexible automation system is that high investment for customer engineered products or systems, continuous production of variable mixes of products, medium production rates, flexibility to deal with soft product variety. Computerized manufacturing support systems. Objectives of automating the manufacturing support systems are to reduce the amount of manual and clerical efforts in product design, manufacturing planning and control, and the business functions. integrates computer-aided design and computer-aided manufacturing in CAD/CAM. SIM includes CAD, CAM, CAP in the business and the business functions of the firm. What are all the various reasons for the automation? To increase labor productivity, to reduce labor cost, to mitigate the effect of labor shortages, to reduce or remove routine manual and clerical tasks, to improve worker safety, to improve product quality, to reduce manufacturing lead time, to accomplish what cannot be done manually, to avoid high cost of not automating. Is there a place for manual labor in the modern production system? Yes. The two aspects are manual labor in factory operations, manual labor in manufacturing support systems. Manual labor in factory operations. The long-term trend is towards greater use of automated systems to substitute for manual labor. When is manual labor justified? Some countries have very low labor rates and automation cannot be justified. Task is too technologically difficult to automate. Short product life cycle is there. Customer product requires human flexibility to cope with ups and downs in demand, to reduce the risk of product failure, and the labor in manufacturing support systems extends to product designers who bring creativity to the design task, manufacturing engineering who design the production equipment and tooling, manufacturing engineers who plan the production methods and routings, equipment maintenance, programming and computer operations, engineering project work, and management. There are several automation principles and strategies being adopted in manufacturing. One is USA principle and 10 strategies of automation and process improvement, and automation migration strategy. The USA principle: understand the existing processes. Understand the existing process. That is input-output analysis, value chain analysis, charting techniques and mathematical modeling. Simplify the process, reduce unnecessary steps and improves, reduce unnecessary steps and moves. Third one, automate the process. 10 strategies for automation and production systems we discussed. We are going to automation migration strategy. There are 10 popular strategies for automation being widely adopted in manufacturing units. One is specialization of equipment, combination of operations. That means you can do 2-3 operations together so that time and cost is less. Simultaneous operations, performance of the operations. Simultaneously, when one operation is going on here, one operation can be done on that. So on a machine, on a part, we can do one operation here, one operation by another unit head. So simultaneously we can perform more than one operation at the same time. Integration of operations. Operations can be integrated together. We can do the operations in that way. Is integration of operations. Increased flexibility. Flexibility of operations. Whether operation 1 is to be done or operation 2 is to be done is immaterial. We can do any operation any time. It's called as flexibility of operations. Improved material handling and storage. Online inspection, process control and optimization. While at the manufacturing stage itself, complete the online inspection, and by having typical better process control, plant operations control, and finally computer integrated manufacturing. Automation migration strategy for introduction of new products. Phase 1 is manual production. Single station manned cells working independently can be used. Advantage of this is quick to set up and low cost tooling. Phase 2, automated production. Single station automated cells operations operating independently can be used. As demand grows, the automation can be justified. Stage 3, where automated integrated production system is used. Multi-station system with several operations and automated transfer of work units between the stations is. You see here, this is the automation migration strategy, where you do start in the phase 1 with of the product development as initially as manual production, then later on move to automated production, that later on automated integrated production system, where the probably the demand come to a standstill position. You can achieve that. Till that it is continuously learning curve, and continuously it is a growing stage, and when the number of product demand is increasing, you have to move to ordinary manual machining to automated machining systems. Let us just discuss to know the product and product processes required for a product and product complexity. This example, let us see. If you see in this example, this is a simple part. This is another simple part being fabricated by plastic blow molding process, and this is a nut bolt arrangement in which we have a screw threads on this, and it is done by 2 or 3 manufacturing operations to perform that. And if you take this product, it is comprising of so many parts. Each part has several operations to have, and the complexity of this product is very high because it is comprising of so many parts, and each part is having so many operations. And if you wanted to calculate the total number of operations for this product, we can easily calculate that, and how complexity it is, you can see. See in this, if P is the product variety and Q is the product quantity, and NP is number of parts in the product, and NO is number of operations in the product. Number of operations in the product multiplied by the number of parts in the product, which is multiplied by Q and P, gives you the total number of operations. The total number of products in one product, in one unit, you can see that QF is equal to P into Q, where the total number of parts produced in NPF is equal to PQ into N. So this is a factory operations model of product specific number of operations required in a product. You can see that. Here if you see, there are several practically available parts, and total number of components that each part is having approximately is listed below. You take a mechanical pencil, it has got approximately 10 number of parts. Ball bearing, modern ball bearing is comprising of 20 parts. Sewing machine, it is comprising of 150 parts. Bicycle chain comprising of bicycle and chain, this is comprising of 300 parts. Automobile, modern automobile is having around 20,000 parts. Commercial aeroplane is having around 1 lakh component. Commercial airplane modern is around 10 lakhs of components. Space shuttle is around 1 crore of components it is having. And the variety of manufacturing processes that are used to manufacture these components, certain components are listed here. Simply take washer, stamping is one process used. Washer, plated steel, stamping and electroplating is used. Pump shaft, machining is used. Coated carbide cutting tool, pressing, sintering and coating grinding is used. Pump housing, casting, machining is used. Like this, there are all a variety of operations that are required to do that, and number of operations, also processing operations, are also listed here. This is to know the complexity of the parts, number of operations on parts, and so many of parts per component or per product. You can have a glance through this. Now let us discuss about the important metrics or matrices of manufacturing or mathematical models of manufacturing. How do we relate to manufacturing lead time? How do we know production rate, all the things, utilization, plant capacity, These are all the various terminologies that are required to know before we know anything about manufacturing. Production rate, plant capacity, production capacity, utilization, availability, manufacturing lead time, work in process, these are all various components of interest to know about manufacturing. And cycle time, let us a typical cycle time for a production operation is T0 is equal to T0 or TC is equal to T0 plus TH plus TH. TC is cycle time, which is comprising of processing time for the operation, handling time, loading unloading of the machine and other things, loading, and TTH is the tool holding time, the time to change the tools, like that. Batch production is TB is setup time plus let us say Q is the batch size and TC is cycle time, then setup time plus total time of operation is called as batch time. The average time per week per unit is TP is equal to TB by TQ. TB by Q. Production rate is 1 by TP. Job shop production, if Q is equal to 1, then TP becomes TSU and plus TC. For quantity of high production, RP is equal to RC is equal to 60 by 1 by TP. T setup by Q is approaching to 0 at the time. Flow line production is TC, the cycle time is equal to transfer time plus maximum operation time, and RC is the production rate of the flow line is 60 by TC, so many components per minute or per hour. Production capacity, plant capacity for facility in which parts are made in one operation. Let us say NO is equal to 1. PCW is N into SW into HS into RP. SW into HS is total number of shifts and hours per shifts. Total number of shifts per week and hours in each shift, HS is equal to. So total number of hours in each week multiplied by production rate multiplied by so many number of facilities, and that gives you the plant capacity, PCW. Plant capacity for a facility in which parts require multiple operations. Normally this plant capacity for a discrete manufacturing would be different, because discrete manufacturing is having multiple operations. Hence PCW for a discrete manufacturing unit is N SW HS RP by NO, where NO is number of operations in the root. And simply this NO does not fall in process plant, like a plant like production capacity of a cement plant, production capacity of paper plant. All these equations holds good. Now the utilization is output by the plant capacity. So U is equal to Q divided by PC, where Q is the quantity actually produced and PC is plant capacity. Normally PC is much more bigger than Q, so utilization is always less than 100%. And if it is 100%, it is remarkable. If it is less than 10%, it is poor performing, and less than 30% is poor performing. We have to have control these parameters and see the utilization is reaching more and more, attaining more value. Availability, A is one parameter which is a statistically measured parameter. A is availability parameter, which is mean time between failure to mean time to repair. So that is the time available. So mean time between failure minus mean time to repair divided by mean time between failure. If this factor is there, then this is called as availability. If availability is equal to 1, that means MTTR is almost 0.
1 minute, sir.
is 0. So MTBF by MTBF equal to 1. That is almost is, it may not be possible also, but is to be achieved. You can see that availability is MTTR and MTBF, equipment operating. This is the time required for equipment operating. That's why availability is MTBF minus MTTR by MTBF. And mean manufacturing lead time MLT is equal to N0 into TSU plus QTC plus TNO. This is a very popular equation. And work in process is availability into utilization into plant capacity MLT divided by SW into HS. And this WIP is one parameter which indicates the wealth of the organization, because work in process is more, that is indicating that inventory is unnecessarily lying on the shop floor, and the shop floor may incur losses, and WIP must be minimum as least as possible, but certain WIP is required in order to have a continuous production system because of the disturbances. If the production systems fall because of non-availability of WIP, again production system under starvation condition, and it cannot produce parts. So minimum WIP is required. We call that as constant work in process constant work in process inventory is maintained. If the more WIP is there, then the inventory holding cost is more, and company is incurring losses. The costs of manufacturing operations. Normally these costs are divided into two components. The total cost of a product being manufactured is divided into fixed cost as well as variable cost. The total cost is sum of fixed cost plus variable cost multiplied by the quantity. Total cost is TC. Fixed cost that remain constant for any output level. Fixed cost is due to the cost incurred for building, equipment, the taxes levied, and other things. Whereas variable costs associated with the cost of the material, cost of the labor, cost of the tools, all the things put together comes under variable cost. Cost of the manufacturing method being employed. So total cost is equal to fixed cost plus variable cost multiplied by Q. In this typical graph, you can see that same product with quantity Q is manufactured, one by manual method, the other by automated method. If it is manual method, its fixed cost is less, that is FC1, and variable cost is increasing with quantity Q. Like you can see, this is the total cost of that manual method is TC1 is equal to FC1 plus VC1 into Q. For the same Q, if it is manufactured by automated means, automated method, its fixed cost is mean because of the automation equipment. So TC2 is FC2 plus VC2 into Q. This graph is different, and this graph is different. These two intersect at one point, because variable cost is increasing in manual methods with quantity Q, because labor is increasing, more labor is used, and other things. Whereas here the labor component is less, that's why its rate of increase is less, but the small. So slope of this curve is very small. And TC2 curve is with less slope, straight line, and TC1 curve is straight line with high, and that's how the high rate. These two curves will intersect at one point, that we call it as a break-even point, and it indicates clearly that point the production quantity, which we can call it as a break-even quantity. If the production quantity, beyond that production quantity, if you wanted to produce, you adopt automation. Less than that quantity, break-even quantity, if you wanted to produce, you better adopt a manual method. It's a clear indication for decision maker. Manufacturing costs Alternative classification of manufacturing costs are how these are all. That direct labor, wages, benefits to paid to the workers, material, cost of raw materials, overhead charges, all other expenses associated with the running of the manufacturing firm, factory overheads, corporate overheads, etc. comes under that. Typical manufacturing costs involved are, to take manufacturing cost itself, we have direct labor, plant machinery, depreciation and energy. It is occupying 26% of the total manufacturing cost. Indirect labor, which is occupying 12% of the cost, and parts and materials is 50% cost. Remaining 50, direct labor, indirect labor, plant and machinery. This is the total manufacturing cost. And total manufacturing cost is only the 40% of the total selling price of the product. What are other components that are added to this are, if the selling price is say 100 rupees, the 40 rupees is manufacturing cost, and 15 rupees is engineering cost, and 5 rupees is R&D, research and development cost, and administration and marketing, etc., comprising of 25 rupees, and the profit margin of 15 rupees is normally added if the selling price is kept as 100, and only 40% is normally as the manufacturing cost. The overhead rates, factory overhead rates, FOHR. FOHR is equal to FOHC divided by DLC, direct labor costs. Factory overhead cost divided by direct labor cost is FOHR. These are all mentioned as a rate function. Corporate overhead is COHC divided by DLC. And hourly cost of worker machine systems, we can use this equation for the cost of equipment usage. C naught is equal to CL into 1 plus FOHRL plus CM into 1 plus FOHRM, where CM is machine rate, so many rupees per hour or dollars per hour. C naught is hourly rate, which is so many dollars per hour. CL is labor rate. And this is one important equation where you can compare two systems. One is manufactured under using direct one set of labor, and the other one is different set of labor. You can use it to compare the system being evaluate the system done by manual means. Let us now discuss this further with a worked out example. This worked out example, you can read it through this. I would like to read it again. Here the ABC company is planning a new product line and will build a new plant to manufacture the parts for a new product line. The product line will include 50 different models. Annual production of each model is expected to be 1000 units. Each product will be assembled of 400 components. All processing of parts will be accomplished in one factory. There are an average of 6 processing steps required to produce each component, and each processing step takes 1 minute, including an allowance for setup time and part handling. All processing operations are performed at workstations, each of which include a production machine and a human worker. If each workstation requires a floor space of 250 meters square, and the factory operates one shift to 2000 hours per year, determine how many production operations, how much floor space, how many workers will be required in the plant. So it's very direct equations. With our previous knowledge, we can easily calculate this. The problem neglects the effect of assembly time, and total number of operations are P, Q, N, P and O. P is 50 product variety and quantity is 1000, so 50 multiplied 1000 multiplied by 400 multiplied by 6 equal to 20 millions operations in a factory per year. Total operation time is 120 into 10 power 6 operations multiplied by 1 minute per operation. See in hours, so many 2 million hours per year. At 2000 hours per year per worker, W is equal to 1000 workers are required. And number of workstations, you have to have one worker for one workstation, so 1000 workstations. Total floor space is Each workstation occupies 250 meters square per workstation. So 1000 workstations includes 250,000 meters square. The total area required for the plant exclusively for operation plant only, it is 250,000. Other plant facilities for the other common services, etc., which includes another 40% of the space is added to that. That includes your total plant space required. And manufacturing capability, total processing capability, the availability set of manufacturing processes, physical size and weight of the product, production capacity, production quantity that can be made in a given time. So this ends the lecture, and we have discussed so far in this lecture that initially we have given a brief introduction about the history of manufacturing, how manufacturing was started, and later on we have discussed the classification of manufacturing systems, job shop, mass production and batch production systems, and also the levels of automation, use of automation, and automation strategies we have discussed, and how the system is moved from this thing, from initial concept to this one we discussed, and we also discussed certain mathematical models of the work units, and this whole lecture gives you the entire concept of production systems. With this knowledge, we can move further to discuss the systematic approach for computer integrated manufacturing. Now, any questions?
What kind of layouts are used for discrete manufacturing systems?
Okay. The question is, what kind of layouts are used for discrete manufacturing systems? We know that there are several kinds of layouts existing. One is fixed position layout, process layout, it looks like this, cellular layouts, and product layout. Now in this diagram you can see that discrete manufacturing industries have been classified into job shops, batch production or cellular manufacturing systems, or mass production systems. In mass production system, product layout is used because the sequence of operations are fixed. Hence, the machines are kept side by side in a line fashion or a looped fashion, and the product or the raw material is launched at first station and a finished product is received at the last station. In the product layout, the workflow starts at the first station. Raw material is launched at first station, and processing is done on the raw material at each station, and at the end of this line you get the finished product. Hence, this is used in mass production systems. Coming to cellular layout or process layouts, batches are launched in these layouts. A batch of 50 or 100 parts are launched, and different machines are used to process different batches. Thus, for a batch production system, process layout or a cellular layout is most appropriate. You know, in job shop industries, job shop means the product is only one variety, but product varieties are different. A job shop can produce different kinds of products. Thus, in a job shop industry, it can be a fixed position layout or a process layout. If you take aircraft production or space shuttle production or ship production, that all belongs to job shop industries only. they will be placed at one point because difficulty to transport this kind of huge structure, that will be placed at one point, and all the other parts will come to that place and get assembled into one single product. This is true for huge products like aircrafts, ships, satellites, etc. Some job shops like machine tools can be processed in process industries, because machine tool is produced maybe in batch of few sizes, like a batch of 10 or 5 in number can be produced. That's how this can be transported to the various machines in a process layout. Thus, job shop systems can use process layouts or fixed position layouts. Any other questions, please?
Yes, sir. What is scrap and how does it affect production rate in batch and flow line production system?
Very good question. What is scrap and how is it affect the production rate in batch and flow line production systems? We all know that scrap, we sometimes call any waste is scrap. Similarly, when you launch a product, it has to undergo a lot of processes. A raw material is taken and it is kept in a first machine to get 1, 2, 3 operations, let us say. When any operation goes wrong due to various reasons, because of the mistake of the human operator or location errors or anything, the kind of tolerances or the kind of requirement specifications we don't achieve. The required specifications we won't achieve. Hence, this particular part will not be functioned as an original part in the field. Hence, it has to be considered as waste. But we have already incurred some money. How? Raw material is costing something and it gets processed on machine. So machine time has been spent on that, and some money is invested into that, but the part has gone wrong. So this has considered as scrap in the production system. If a machine produces some scrap, it can be due to various reasons, because of the machine is not able to produce the confirmation of the tolerances. Sorry, take 2. The reasons for production of scrap are many. Sometimes the machines are not functioning properly. In order to reduce scrap, we need to maintain the machines at high levels. We need to have preventive maintenance strategies. We should not give scope for the machine to get failed while it is performing a typical operation. If it fails while it is in operation, that part may goes into scrap. Thus, preventive maintenance strategies and other technological strategies are required to reduce scrap. For example, you take these equations. Already the equations have been discussed at large. In a batch production industry, the batch time TB is TSU plus QTC, where Q, capital Q, is the batch size. TC is the cycle time or the operation time on that particular machine. And the average production time per work unit is TP is equal to TB by Q. I will explain. So in this equation, batch time is equal to setup time plus the batch size multiplied by the cycle time. In this, suppose if scrap is there, that means if you launch 100 parts as a batch size, you won't get 100 parts. Suppose if you allow 2% of scrap, you may get 98 parts only. Suppose you wanted to get 100 parts, batch size of 100, you have to launch with 100 divided by 0.98 number of parts. It may be coming around 1 or 3 or like that. So it indicates that few parts have to be considered as wastage and the remaining parts only will come into Q. So you have to produce more number of parts than what is required if you allow scrap rate. And so much of amount of money for each scrapped item is costing to you. Thus, total TB becomes now TSU plus Q by 1 minus Q TC, where Q is scrap rate, and you have to minimize this Q as much less as possible. If it is more, automatically TB becomes more, and TP, production time, is equal to TB by Q. This becomes more, and the production rate is equal to TB by 1 by TB, which is Q by 1 minus Q by TB. Thus production rate is reduced if you allow scrap rate, and scrap rate need to be reduced. Suppose the scrap in the flow line scrap is not permitted. If a scrap comes out, it can be off at any stage. At any of these machines which are under processing, say these are all machines or workstations, they are processing this part, and it can produce scrap, or it can produce scrap, or it can produce scrap, or anything. And ultimately, when you get the component out of this line, it may be with scrap or without scrap. There are several methods existing to study the effect of scrap on this. Thus, we should be very cautious not to allow any scrap here. If scrap comes, it should be done at various inspections, or level inspection stations are used here, and those will remove those parts and produce that. The yield will be reduced. The yield of the line is reduced. Total line yield, so let us say it is 100%. It won't be 100% if you use scrap there. That means if you allow scrap there, it is going to be around 90% or 95% like that.
Sir, how do you quantify plant capacity in various process manufacturing industries and discrete manufacturing industries? Please explain.
How do you quantify plant capacity in various process manufacturing industries and discrete manufacturing industries? Let us see what we call as process manufacturing industries. You take a cement plant, you take a power plant, or you take a petroleum plant, where the output is either the petroleum or the power or the cement, a single unique output, and the input is also very confirmed input is given, like raw material, 1-2 kinds of raw material is given as input. But the output is unique only here in all these industries. You take a paper industry, paper is only the output. So the capacity is measured in these process industries. Yes, how much is the output per day? Like so many tons of paper production in one day, so many megawatts of power generation in a day, or in one week, or in one fortnight, or in 1 month. So much of tons of petroleum is produced, petrol is produced or diesel is produced per day or per week. Like this, the plant capacity is estimated in process industries. In process industries, the plant capacity is estimated as so many tons of output or so many units of output per day or week. Comes to a machine tool industry, or a car manufacturing industry, or a aircraft appliances industry, or anything. They are all discrete manufacturing industries. The products are discrete in nature. So we don't measure the capacity in terms of output. Like we cannot produce one aircraft in a day. So 0.5 aircrafts per day or one machine tool in 1 month. We cannot give this kind of description, because the industry can produce machine tool of one variety and next day it can produce different variety of machine tool, because they can be a batch or job shop or anything. The output could be different, and inputs, depending upon the outputs, inputs could be different. Hence the plant capacity cannot be described as output per day or per week. How do we give the plant capacity then? Plant capacity is estimated as man machine hours. How many number of workers are working in that industry? How many shifts that particular industry works? Or how many machines are working? And what is the total man machines available in one shift, or in a fortnight, or in 1 month? So like that, the plant capacity as given or as estimated as the capacity in terms of man and machine hours. So the plant capacity is estimation or quantification is different for process industry and discrete manufacturing industries.
So my question is, how do we calculate selling price in a typical manufacturing industry?
Next question is, explain how do we calculate selling price of a typical manufacturing industry. You take this slide. If you see the slide, the components of selling price are included. The components of selling prices include manufacturing cost, engineering cost, R&D cost, administrative, sales, marketing costs, and profit. In fact, the major play of selling price is manufacturing cost. Manufacturing cost in terms include direct labor, plant and machinery costs, indirect labor, and material cost, tool costs, etc. So it is estimated that total selling price, in the total selling price, if you give a 15% as profit and 40% is the manufacturing cost, and 15% is only design or engineering cost, and R&D, you must have to give R&D cost as 5%, and administrative salaries or marketing people salaries and other expenditures comes under administration, sales, marketing, sales, etc. Total cost is manufacturing cost, engineering cost, R&D cost and administrative cost plus profit gives you the selling price. This is how it is estimated in a manufacturing industry.